Hello everyone. Let's review a few ideas with simple harmonic motion, how it relates to rotational and circular motion, and a few objects that undergo simple harmonic motion, like masses on springs, torsion bars, and pendulums. Here you see an example of simple harmonic motion of a mass on a spring, and that mass is allowed to oscillate up and down. The displacement, velocity, and acceleration curves are shown here also as a function of time. Displacement, as we saw in class, is found by multiplying A times the cosine of omega times t, where A is the amplitude or maximum x displacement from its rest position, and omega is the rate change of theta with respect to time, which is also angular speed in rotational quantities, and t is the time. This is a cosinusoidal curve, and you can see that by that trace that it's making. The velocity is found by taking the derivative of x with respect to time, and when we do that we'll get negative a omega sine of omega times t, and this is a sinusoidal curve. We'll get the maximum velocity when sine theta is equal to 1, and that occurs at the pi over 2 and 3 pi over 2 marks there. And Vmax is also then found as negative a times omega, the negative amplitude times that angular speed. We also see then the acceleration curve there. You can find the acceleration by taking the derivative of the velocity with respect to time. When you do that, you'll get negative a omega squared times the cosine of omega times t. This is a cosinusoidal curve again. Here we've got a max is at the top and the bottom of the swing. This occurs at that maximum x position, or the amplitude points. Here we are looking at the simple harmonic motion of a mass on a spring and how it relates to circular motion. If we take a look at the unbalanced force acting on the mass on the spring, that unbalanced force is the restoration force, and if you remember, that restoration force is Hooke's law, or minus k times x. So ma is equal to minus k times x. We could substitute in our maximum acceleration expression, so we get m times that quantity of negative omega squared times x max, and that equals negative k times x max. If we solve for omega squared, we'll get k over m, or omega is going to be equal to the square root of k over m. Now that's a useful expression that's not on the equation sheet. So omega is equal to the square root of k over m. That really will give you that angular frequency or that angular speed of a mass on a spring. Angular frequency is also denoted by omega, or omega is sometimes called that angular frequency, and it's found by 2 pi times the linear frequency. So the linear frequency will be omega over 2 pi, and if we substitute in our expression that we just found for omega, square root of k over m, we'll get the linear frequency is 1 over 2 pi times the square root of k over m. Remember, linear frequency is the number of cycles per time, or revolutions per time. If we want to find the period of a mass on a spring, we take 1 over the frequency, so the period t, capital T there, will be equal to 2 pi times the square root of m over k. We can also relate the acceleration in this simple harmonic motion to the centripetal acceleration. If we take that maximum acceleration as omega squared times x, and we substitute there for omega 1 complete revolution, that distance is 2 pi, over the time, which is 1 period, we'll get 4 pi squared over period squared times that distance x. And then we relate that to circular or centripetal acceleration, if you remember, as 4 pi squared r over t squared. So you can see the similarity between those two expressions. We looked at 3 simple harmonic motions, and here I've got the 3 set up right now for you. The mass on a spring, we have a torsion spring, sometimes called a torsion pendulum, and then we also have a regular pendulum with the mass at the end of a string. Each one of these has a function for their period. We just saw that the period of a mass on the spring is 2 pi times the square root of m over k, where m is the mass and k is the spring constant. The torsion pendulum, or the torsion spring, is very similar. It's bound by 2 pi times the square root of I over kappa, where I is the moment of inertia. That's the mass synonymous quantity in rotation. And we also have kappa, which is the spring constant for a torsion spring. The regular pendulum, which is a mass at the end of a string, we've got its period is equal to 2 pi times the square root of L over G. That period is calculated by looking at torque, moment of inertia, angular acceleration, and angular velocity or angular speed. And I encourage you to take a look at that derivation in your book. I won't go through that whole thing right here. But all three of these we've taken a look at. What's interesting also is that the regular pendulum here depends on the acceleration of gravity. So that's going to depend on where you are in the universe, what planet or moon you are on, to determine that period. The other two do not. It only depends on the spring constant and basically the mass that is on that spring. So you can take these anywhere and get that same period. As we just said, the period of springs does not depend on the acceleration of gravity, which makes them very useful in space. We can use these springs to determine the mass of objects in space. If we have some known masses, we can take a look at what that period is. We can also get to the spring constant. We can then put some unknown masses on here and determine what those masses are. And we saw this earlier in the year with the space shuttle, massing objects out on the space shuttle. They had the small mass spring scale, and then they also had the large mass spring scale that they could use to get their body mass as well. Well, I hope this podcast has helped you review the ideas of simple harmonic motion. As always, you can ask questions in class, and good luck on the test.